Thermal power plants, a comprehensive overview. Thermal power plants are one of the most widely used energy generation systems in the world, playing a crucial role in meeting global energy demands. These plants operate by converting heat energy, derived from burning fuels or harnessing nuclear reactions, into mechanical energy, which is then transformed into electricity. As the backbone of modern industrial and residential power supply, thermal power plants have evolved significantly since their inception. This video explores the workings of thermal power plants, their various types, advantages, and disadvantages, along with a discussion of emerging technologies and their future prospects in the energy landscape. By understanding the role and impact of thermal power plants, we can appreciate their importance while seeking ways to improve their efficiency and sustainability. A thermal power plant is a facility that generates electricity by converting heat energy into electrical energy through a series of processes. The heat is typically produced by burning fossil fuels such as coal, natural gas, or oil, or through nuclear reactions. This heat is then used to produce steam, which drives turbines connected to generators, ultimately producing electricity. The fundamental working principle of a thermal power plant is based on the Rankine cycle, a thermodynamic process where heat energy is used to convert water into high-pressure steam. This steam is then expanded through turbines, generating mechanical energy. The mechanical energy is subsequently converted into electrical energy using a generator. Boiler or steam generator converts water into high-pressure steam using the heat from fuel combustion. Turbines, rotational devices powered by the steam to generate mechanical energy. Generator converts the mechanical energy from the turbines into electrical energy. Condenser cools the used steam and converts it back into water for reuse. Cooling towers dissipate excess heat to maintain system efficiency. Thermal power plants operate on the principle of converting heat energy into mechanical and electrical energy. This process involves several key stages, beginning with fuel combustion and ending with electricity generation. The entire operation is based on the thermodynamic Rankine cycle, where heat is used to produce steam that drives turbines. The process starts in the boiler or steam generator, where fuel, typically coal, natural gas, or oil, is burned to produce heat. This heat converts water into high-pressure steam. The efficiency of the boiler is critical, as it determines how effectively the thermal energy from the fuel is transferred to the steam. Advanced boilers are designed to minimize energy losses and maximize output. Next, the high-pressure steam flows into a steam turbine, where it expands and cools, causing the turbine blades to rotate. This mechanical rotation is the core source of energy that will be converted into electricity. Steam turbines are engineered to handle the extreme pressure and temperature of the steam, ensuring optimal performance and durability. The mechanical energy produced by the turbine is transferred to a generator, where it is converted into electrical energy through electromagnetic induction. Generators are equipped with a rotor and stator that work together to produce electricity as the turbine rotates. This electricity is then transmitted to the grid for distribution. After passing through the turbine, the steam is directed into a condenser, where it is cooled and converted back into water. The cooled water is then recycled into the boiler to complete the cycle. Condensers use either air or water as a cooling medium, and their efficiency significantly affects the overall performance of the power plant. Finally, cooling towers or other heat dissipation systems are used to expel the excess heat generated during the process. This step ensures that the plant operates within safe temperature limits and maintains efficiency. Some plants also integrate systems like carbon capture and storage, CCS, to reduce environmental impact. In summary, thermal power plants function as complex systems that efficiently convert heat energy into electricity, with each component playing a vital role in maintaining operational efficiency and reliability. While they remain a cornerstone of global power generation, advancements in technology continue to improve their sustainability and reduce their environmental footprint. Thermal power plants can be categorized based on the type of fuel they use and their design. Each type has unique features, operational methods, and environmental impacts. Below is an overview of the major types of thermal power plants. Coal-fired power plants are the most traditional and widely used thermal plants. They generate electricity by burning coal to produce heat, which converts water into high-pressure steam. This steam drives turbines to generate electricity. Coal plants are known for their reliability and large-scale energy production capabilities. However, they are also criticized for their high greenhouse gas emissions and environmental impact, such as ash disposal and air pollution. Modern coal plants often integrate emission control technologies to mitigate these issues. Natural gas power plants use gas turbines to generate electricity, either in a simple cycle or as part of a combined cycle setup. In combined cycle plants, the waste heat from the gas turbine is used to generate additional power through a steam turbine, significantly improving efficiency. These plants are considered cleaner and more efficient than coal-fired plants, producing less carbon dioxide and almost no sulfur dioxide. They are particularly favored in regions with abundant natural gas resources. Oil-fired power plants use oil as the primary fuel to generate heat. Although they were more common in the past, their use has declined due to higher fuel costs and environmental concerns. These plants are generally used as backup power sources or in areas where other fuels are not readily available. Oil plants have the advantage of quick startup times, making them suitable for meeting peak energy demands. Nuclear power plants differ from conventional thermal plants because they use nuclear fission reactions to produce heat. Uranium or plutonium is used as fuel, and the energy released during fission heats water to produce steam. Nuclear plants are highly efficient and generate large amounts of electricity with minimal greenhouse gas emissions. However, they require stringent safety measures and careful management of radioactive waste. Geothermal power plants harness heat from the Earth's interior to produce electricity. These plants are typically located in regions with high geothermal activity, such as volcanic areas. Geothermal plants are renewable and produce minimal emissions, but their use is limited to areas with accessible geothermal resources. Biomass-fired power plants use organic materials like wood, agricultural waste, or dedicated energy crops as fuel. These plants are considered renewable and can help reduce waste by repurposing it for energy production. While they produce less carbon dioxide compared to fossil fuels, their sustainability depends on responsible sourcing and efficient combustion technologies. Waste-to-energy plants convert municipal or industrial waste into electricity through incineration or gasification. These plants serve a dual purpose by managing waste and generating energy. However, they require advanced emission control systems to prevent the release of harmful pollutants. Each type of thermal power plant has its advantages and disadvantages, often influenced by factors such as fuel availability, efficiency, cost, and environmental impact. The choice of a thermal power plant type depends on regional resources, energy policies, and environmental considerations, fuels and technological advances in thermal power plants. The type of fuel used in a thermal power plant plays a crucial role in determining its efficiency, cost-effectiveness, and environmental impact. Thermal power plants rely on a variety of fuels, ranging from traditional fossil fuels to alternative renewable sources. Here are the main fuels commonly used. 1. Coal. Coal is the most widely used fuel in thermal power plants worldwide. It is favored for its abundance and relatively low cost. Coal-fired plants burn coal to produce heat, which is used to convert water into steam for driving turbines. Despite its economic advantages, coal combustion is associated with high greenhouse gas emissions, including carbon dioxide, sulfur dioxide, and particulate matter. Modern coal plants often employ emission control technologies such as flue gas desulfurization and carbon capture to mitigate environmental impacts. 2. Natural gas. Natural gas is a cleaner and more efficient alternative to coal. It is used in gas turbines or combined cycle plants, where the heat from gas combustion drives a gas turbine and the exhaust is used to produce steam for a secondary turbine. This dual process significantly improves efficiency. Natural gas plants emit fewer pollutants, making them a popular choice for reducing the carbon footprint of electricity generation. However, reliance on natural gas depends on its availability and stable pricing. 3. Oil. Oil-fired power plants are less common, but are still used in areas where coal and natural gas are scarce or expensive. They burn liquid fuels like diesel or heavy oil to generate heat. These plants are typically used as peaking power plants due to their ability to start quickly and provide energy during high-demand periods. However, they are costly to operate and emit a significant amount of greenhouse gases, making them less desirable in long-term energy strategies. 4. Nuclear fuel. Nuclear power plants use uranium or plutonium as fuel to generate heat through the process of nuclear fission. A small amount of nuclear fuel can produce an immense amount of energy, making these plants highly efficient. Unlike fossil fuels, nuclear fuel does not produce greenhouse gas emissions during operation. However, managing radioactive waste and ensuring the safety of nuclear reactors remain major challenges. 5. Biomass. Biomass includes organic materials such as wood, agricultural residues, and dedicated energy crops. When burned, biomass releases energy similar to fossil fuels, but with a smaller net carbon footprint because the carbon released is offset by the carbon absorbed during the growth of the biomass. Biomass-fired plants are considered renewable and sustainable, provided the sourcing of biomass is managed responsibly. They are increasingly being used to replace coal in some regions. 6. Geothermal heat. While not a conventional fuel, geothermal heat is a renewable energy source used in geothermal power plants. Heat from the Earth's interior is harnessed to produce steam, which drives turbines. These plants do not burn any fuel, making them environmentally friendly, though their use is limited to areas with accessible geothermal resources. 7. Waste. Municipal and industrial waste is converted into energy in waste-to-energy plants. This method reduces landfill waste and provides an alternative energy source. The waste is incinerated or gasified to produce heat, which generates steam for electricity production. While this reduces dependence on fossil fuels, managing emissions from waste combustion is critical. 8. Hydrogen. Hydrogen is an emerging fuel for future thermal power plants. When burned, hydrogen produces only water as a byproduct, making it a zero-emission fuel. While still in the experimental and development stage for large-scale power generation, hydrogen holds promise for creating cleaner thermal energy systems. In conclusion, the choice of fuel for thermal power plants depends on factors such as availability, cost, and environmental impact. The global energy landscape is shifting toward cleaner and renewable fuels, with innovations aimed at improving efficiency and sustainability while minimizing environmental harm. Thermal power plants play a vital role in global electricity generation due to their ability to produce large amounts of energy. However, they come with their own set of advantages and disadvantages, which influence their use in different regions and energy policies. Reliable and consistent energy supply. Thermal power plants are capable of operating continuously, providing a stable and reliable source of electricity. Unlike renewable energy sources like solar or wind, which depend on weather conditions, thermal plants can produce power 24/7. High energy output. These plants can generate a significant amount of electricity to meet the needs of large populations in industrial sectors. This makes them ideal for regions with high energy demands. Flexible fuel options. Thermal power plants can use a variety of fuels, including coal, natural gas, oil, and biomass, depending on availability and economic factors. This flexibility allows plants to adapt to different energy resources. Established technology and infrastructure. The technology for thermal power generation is well established and widely understood, making it easier to set up and maintain. Many countries already have the infrastructure in place for thermal plants, reducing initial investment costs. Cost-effective for large-scale energy production. While initial setup costs can be high, the operational costs are relatively low for large-scale electricity generation, particularly in regions with abundant fuel resources like coal or natural gas. Environmental impact. Thermal power plants are major contributors to greenhouse gas emissions, including carbon dioxide, sulfur dioxide, and nitrogen oxides, which contribute to climate change and air pollution. Additionally, coal-fired plants produce ash and other harmful waste byproducts. Non-renewable resource dependence. Most thermal plants rely on non-renewable fuels like coal, oil, and natural gas, which are finite resources. This dependence creates long-term sustainability challenges and vulnerability to fuel price fluctuations. High water usage. Thermal plants require large amounts of water for steam generation and cooling. This can strain water resources, particularly in regions prone to drought or water scarcity. Initial capital costs. Building a thermal power plant requires significant investment in infrastructure, including boilers, turbines, and cooling systems. While operational costs may be lower, the initial setup can be a barrier for some regions. Health and safety concerns. The combustion of fossil fuels releases pollutants that can have serious health effects on nearby communities, including respiratory issues and cardiovascular diseases. Furthermore, nuclear thermal plants pose risks related to radiation exposure and potential accidents. Waste management issues. Disposing of byproducts, such as ash from coal-fired plants or radioactive waste from nuclear plants, poses environmental and logistical challenges. Improper disposal can lead to contamination of land and water resources. Thermal power plants have seen significant technological advancements over the years, aimed at improving efficiency, reducing environmental impact, and optimizing operational costs. These innovations have been driven by the need to meet growing energy demands while adhering to stricter environmental regulations. 1. Supercritical and ultra-supercritical technology. One of the most notable advancements in thermal power plants is the adoption of supercritical and ultra-supercritical (USC) technology. These systems operate at higher temperatures and pressures than traditional subcritical plants, increasing the thermal efficiency of power generation. By extracting more energy from the same amount of fuel, these technologies reduce fuel consumption and greenhouse gas emissions. They represent a significant step toward making thermal plants more sustainable. 2. Carbon capture and storage, CCS. Carbon capture and storage technology is a groundbreaking solution aimed at reducing the carbon emissions of thermal power plants. CCS systems capture carbon dioxide produced during fuel combustion and store it underground or use it for industrial purposes, such as enhanced oil recovery. While CCS is still being developed for widespread use, it holds great potential for decarbonizing thermal power generation. 3. Integration of renewable energy sources. Modern thermal power plants are increasingly integrating renewable energy sources, such as solar or biomass, into their operations. Hybrid plants, for example, combine solar thermal energy with conventional fossil fuel systems to reduce reliance on non-renewable resources. This approach not only enhances sustainability, but also improves plant efficiency by utilizing multiple energy sources. 4. Improved boiler and turbine efficiency. Advancements in boiler and turbine technology have significantly boosted the performance of thermal power plants. Modern boilers are designed to reduce heat loss and operate at higher temperatures, while advanced turbines feature improved aerodynamics and materials that can withstand extreme conditions. These innovations contribute to increased power output and reduced operational costs. 5. Smart plant automation and digitalization. The adoption of smart plant automation and digitalization has revolutionized the way thermal power plants operate. Advanced control systems, sensors, and data analytics enable real-time monitoring and predictive maintenance. Digital twins, which create virtual models of power plants, are being used to simulate operations and test improvements without disrupting actual performance. 6. Fluidized bed combustion, FBC technology. Fluidized bed combustion is an innovative technology that enhances the efficiency and environmental performance of coal-fired power plants. By burning fuel in a fluidized bed of air and particles, FBC systems achieve lower combustion temperatures, reducing nitrogen oxide emissions and improving fuel flexibility. This makes it possible to use low-grade fuels like biomass or waste. 7. Waste heat recovery systems. Waste heat recovery systems capture and reuse the heat lost during electricity generation. These systems are often used in combined cycle power plants, where the exhaust from gas turbines is utilized to generate steam for additional electricity production. By recovering waste heat, plants can significantly improve efficiency and reduce overall emissions. 8. Adoption of hydrogen as a fuel. Hydrogen is emerging as a clean alternative fuel for thermal power plants. When burned, hydrogen produces water as its only byproduct, eliminating greenhouse gas emissions. While the technology for hydrogen-fired thermal plants is still in its infancy, ongoing research and development are paving the way for its adoption on a larger scale. Technological advancements in thermal power plants are transforming the energy landscape, making these facilities more efficient, sustainable, and adaptable to modern energy challenges. These innovations are not only helping thermal plants remain relevant, but are also contributing to global efforts to achieve cleaner and more reliable energy systems. Comparative analysis of power generation methods. Thermal power plants, while a cornerstone of global electricity generation, face increasing competition from other power generation methods, particularly renewable energy sources and nuclear energy. Each power generation method has its unique strengths and weaknesses, which influence its adoption based on factors such as cost, environmental impact, and energy security. Renewable energy sources, such as solar, wind, hydroelectric, and geothermal power, are rapidly gaining popularity due to their environmental benefits and sustainability. Unlike thermal power plants, which burn fossil fuels and emit greenhouse gases, renewable energy methods produce little to no emissions during operation. Solar and wind, for example, generate electricity by harnessing natural resources that are both abundant and renewable. However, thermal power plants have some distinct advantages over renewable energy sources. They can produce a continuous and stable supply of electricity, making them more reliable for meeting baseload demand. In contrast, renewable sources like solar and wind are intermittent, depending on weather conditions and daylight hours. This makes it challenging to ensure a steady supply of electricity without energy storage solutions or backup systems. Another factor is scalability. While solar and wind power can be deployed in smaller, decentralized units, thermal power plants are typically more suited to large-scale generation due to their higher energy output. Additionally, the infrastructure for thermal power plants is already well established, whereas large-scale renewable energy systems may require significant investment in new infrastructure. Nuclear power plants, like thermal plants, generate electricity by heating water to produce steam, which drives turbines. However, instead of burning fossil fuels, nuclear plants use uranium or plutonium in a fission process to release heat. Nuclear plants produce a significant amount of electricity with minimal greenhouse gas emissions, making them an attractive alternative to coal-fired power plants in terms of environmental impact. While nuclear power is clean in terms of emissions, it faces challenges such as high initial capital costs, long construction times, and concerns about safety and radioactive waste disposal. Accidents at nuclear power plants, such as those at Chernobyl and Fukushima, have led to public concerns and regulatory hurdles, limiting their widespread adoption in some regions. In contrast, thermal power plants are less risky in terms of catastrophic accidents, but have a higher environmental impact due to carbon emissions. They also face issues related to fuel availability and long-term sustainability. Nuclear power, despite its challenges, holds potential for cleaner, more efficient energy production in the future, particularly with advancements in reactor technology and waste management. Combined cycle power plants are a more advanced version of traditional thermal plants that utilize both gas and steam turbines to generate electricity. In these plants, natural gas is burned in a gas turbine, and the waste heat is used to produce steam for a steam turbine, improving efficiency compared to a single-cycle thermal plant. Combined cycle plants can achieve efficiencies of up to 60%, significantly higher than the typical 33 to 40% efficiency of conventional thermal plants. The main advantage of combined cycle plants over traditional thermal power plants is their improved fuel efficiency and lower emissions. They are particularly well suited for natural gas, which has a lower carbon footprint than coal. However, combined cycle plants still face challenges related to fuel dependence, and they require complex technology and higher upfront costs compared to traditional thermal plants. Gas turbine power plants are another form of thermal power generation, but they are typically smaller and more flexible than conventional thermal plants. These plants burn natural gas directly in a turbine, producing both mechanical energy and heat, which can be used in a combined cycle plant for greater efficiency. Gas turbine plants can start up quickly, making them ideal for peak load power generation and backup services. While gas turbine plants offer efficiency advantages over traditional thermal plants, especially when used in combined cycle configurations, they are still dependent on natural gas, which can be subject to price volatility and supply constraints. Additionally, gas turbines emit carbon dioxide, although at lower levels than coal-fired plants. In summary, while thermal power plants remain a reliable and widely used source of electricity, they face significant competition from renewable energy sources, nuclear power, and more advanced systems like combined cycle and gas turbine plants. Each method has its advantages and limitations, and a balanced energy mix that includes a combination of these technologies is likely the best approach for meeting future energy needs while addressing environmental concerns. Thermal power plants have been a cornerstone of global energy generation for decades, providing reliable and large-scale electricity to power homes, industries, and economies. Their ability to operate continuously and their well-established infrastructure make them indispensable, especially in regions with high energy demands. However, the environmental challenges posed by thermal power plants, including greenhouse gas emissions and resource depletion, underscore the need for innovation and a shift toward cleaner energy systems. Advancements in technology, such as supercritical and ultra-supercritical systems, carbon capture and storage, and hybrid integration with renewable energy sources, are paving the way for more sustainable and efficient thermal power generation. Additionally, alternative fuels like biomass and emerging options like hydrogen hold promise for reducing the environmental footprint of these plants. While thermal power plants face growing competition from renewable energy and nuclear power, they continue to play a critical role in the global energy mix. Balancing their advantages with efforts to mitigate their disadvantages is essential for achieving long-term energy security and environmental sustainability. As the energy landscape evolves, thermal power plants must adapt to remain relevant and contribute to a cleaner, more efficient future for electricity generation.